Hi, this is Nandika. I'm going to be going over my lab report for Lab 3. So for the introduction, the goals of the experiment for part 1, it was finding the mass of the black hole. So we modeled a star orbiting a black hole using position data generated through our emails. Then we used Newton's second law, F equals dp dt, to calculate the net force on the star at each point. We determined the black hole's mass by assuming the star's motion is caused solely by the gravitational force from the black hole. And then we were able to compare the net, parallel, and perpendicular force components to understand how they relate to the rate of change of the momentum. For part 2, orbit and don't crash, we simulated the moon, planet, and spaceship system where the planet is stationary and the moon orbits it. We find an initial velocity for the spaceship without crashing, and then applying Newton's second law, this time multiplying gravitational interactions, planet ship, moon ship, and then explore orbital stability and gravitational dominance to see which bodies most strongly influence motion. For the findings, the mass of the black hole, 2.44 E3 kg, initial velocity of the spaceship, negative 4.8 E7, 2.5 E6, 0 in meters per second. The key concepts, force net, change in momentum or change in time. This can be written into the velocity update formula, and then the velocity update formula is related to the position update formula. As for the parallel and perpendicular components of the net force, the parallel component is the direction of the motion. The positive p hat axis points in the direction of the motion, and it's related to the change in speed of an object. The perpendicular component points to the center of a turning circle, related to the change in direction. These components can then be added. For the parallel component, it's the change in momentum over change in time. For the perpendicular component, it's mv squared over r, and then times n half direction. Gravitational force, or the universal law of gravitation, it's the gravitational force on an object due to another object, and it's an attractive force defined as the following: negative gm1m2 over r squared times r hat. Negative sign indicates an attractive force. V hat is the unit vector, and then the formula is given. Okay, as for the free body diagram, for part 1, we have the black hole and then the force of gravity on black hole, and then force of gravity on a star. The system is the star, the surroundings are the black hole in space. For part 2, we have the gravitational forces as seen here, the gravitational forces between the black hole and the ship, the gravitational force between the spaceship and the planet. System 2 is the star and the planet, and then surroundings are black hole in space. Here we have the code for part 1. This is the computational model. We have the time interval. Here's some important equations for part 1. We have F net. We have the perpendicular component of net force. Here we have a video of part 1, and the code, as we can see, it's orbiting and then orbiting the black hole, and the arrows point in different directions. And those are the parallel and the perpendicular components of the forces being acted on, the gravitational forces. So for part 2, the computational model, we have the code here, our planet to the moon, which is the moon position minus the planet position, and then we're applying the formula for gravitational force, and then norm here is finding the r hat vector, essentially. Discussion for part 1. Basically, the star follows an elliptical orbit around the black hole due to gravitational force. Gravitational force is smaller in magnitude when the star is further away from the black hole compared to when the star is close to the black hole, shown by the sizes of the arrows in the model, and then the sources of error are getting different values for mass each iteration and for gravitational constant g. For part 2, this is also the code continued. We're finding the ship velocity, the ship position, and then again applying the formula for gravitation. This is our result from part 2. The ideal initial ship velocity is 2.44 times 10 to the power 4, 2.44 times 10 to the power 4, and 0, and that's in meters per second. Similarities and differences between part 1 and part 2. Similarities, both parts use Newton's second law, both rely on universal law of gravitation. Differences, 2-body system versus 3-body system, star mass is unknown and masses are all known. Error, the simulation uses discrete time steps. Velocity is estimated, orbital paths are generated from an approximate ellipse. Discussion question, so for the first one, even though mathematically they're equivalent, calculating rate of change of momentum is often simpler. Net force requires one to account for all external forces. For the second one would need to account for all parts of the surroundings that interact with the system and vice versa. Dominant forces would be those between the star, the moon, and the black hole.